I've just started a recording so that you can have this for later. Yeah, good morning, everyone. Okay, so welcome to Physics 245 recitation. This is the first time that I've ever taught synchronously. So it's a little weird for me. I know I've done office hours, in real time like this, but it is kind of strange. I'm still not used to sitting in an empty room talking to a laptop and trying to maintain coherent thoughts and such. Articulating coherent thoughts. Okay, so let's begin by discussing the syllabus, which you see on your screen. So if you look in the upper left corner, there's a little magnifying, there's a little square, with a little magnify on it. If you click on that, you've got some zoom in and zoom out tools so that you can zoom in and see it a little better. Oh, there was another. Oh, you went into the other room? Okay. Yeah, I meant to close that. Could somebody go into the other room and tell them to come here instead? Yeah, the other room meaning the. Yeah, I see what that means. Okay.
Someone already went in there and said something, which is why we ended up here.
Oh, great. Thank you.
You're welcome.
Morning, Kelly.
Good morning.
Okay, so on the screen then is the syllabus. Let's continue with this then. Basically, we're going to hang out and discuss some physics. So here in number 1, it says, recitation is a time to reinforce basic concepts underlying the course material. Mainly, I will work out and discuss example problems and address your questions. I will also allow time for you to work out a problem or two. By the way, this is the syllabus that I use when I teach in person. And so as we go along and I figure out how to really do this effectively, or as effectively as I can, I may have to adjust what's on the syllabus here. But basically, I'm going to show up and discuss for a few minutes the concepts for that week, and then give you a chance to either work out some problems or give you a chance to do some problems, probably both. And yeah, that's what we're going to do. Let me look at the chat because some activity there. Live stream problems on paper. Yeah, indeed. So I'll show you a little toy that I bought in a moment. About the syllabus, and number 2, your recitation grade will be determined as follows. So Dr. Kroon has asked us recitation instructors to base the grade on attendance, which means I'm not going to be collecting any work or grading any work. We're just going to hang out and do some problems, and hopefully it'll be a time that'll be useful for you. So bring your questions, and we'll hopefully make a time that's useful to you. You'll earn 1 credit per recitation session by arriving on time and demonstrating that you're engaged and making an effort for the duration of the session. Of course, that's easier to do in person. Nevertheless, I'll figure out a way to notate that you're here. There will be 14 sessions. I will count the number of credits you earn and divide by 12. Thus, you can miss 2 sessions and still get a perfect recitation grade. What I just read says that you can miss 2 recitations without it having any effect on your recitation grade. And this is built in so to allow for sickness and accidents and weddings and funerals and jury duty and sports events, etc. And yes, somebody once scheduled their wedding during my recitation session. I didn't get an invitation. Notice that the highest possible recitation grade is 100%. So even if you attend all 14, you're still just going to get 100%. Note that your recitation grade accounts for a rather small portion of your final grade for the course. I was looking at Dr. Kroon's syllabus and I didn't quite understand how he's counting things, but recitation counts for 5. It's not a big portion of your final grade for the course, so please don't sweat it. Let's be casual. Let's try to make this a comfortable and useful time for you and not worry too much about, oh, I missed one, can I make, etc. And losing a lot of sleep over that. If recitation is canceled and no alternative arrangements are made in advance, I don't know about the weather part, but I could certainly be sick, for example, then I will count everyone as being present that day. And except as described in item F that I just read, under no circumstances will credit be given if you actually attend. So no recitation makeups. Having said that, I am recording this, so you can visit it later. I'll hold office hours. I'm not exactly sure when, but certainly by appointment at any time. Feel free to email me. There's a learning assistant, I believe. I don't know who it is. Do you guys know who the learning assistant is? Or have you been told about that? Sai, okay, very good. So you know about that. And then there's also the physics tutor, Dr. Fisher. Here's a little web page that you can go to see his hours and how to contact him. All right, so any questions on sort of the mechanics of what we'll be doing here?
I don't see you drinking coffee. I don't understand. It's in the morning. Shouldn't you have your little, okay.
So I had it already, so.
Perfect.
Do you see me or do you see the
But
syllabus? You see
you're like
both?
a little thumbnail in the bottom corner, so.
Oh, okay. All right, so now let me unshare this this thing. Now you can see me, right? Let me show you my new toy. So look at this tiny little webcam or document camera. Isn't this cute? It was cheap too, and it works reasonably well. So I'm talking about live streaming problems on paper. So maybe this will make that possible. It seems to work, but of course, when I try to do it live, probably something's going to go wrong. So I ask for your patience in advance. Yeah, it looks like the Pixar lamp. That's right. All right. What I want to do now is talk a little bit about the general subject for today, which is waves and, oscillations and waves. So let me share a PowerPoint. There it is. And those of you who were in my class last semester might recognize some of these slides. Yeah, there's a little bit of overlap in the first 2 weeks of this class and my class in the last 2 weeks. So we're going to be going over oscillations and waves and also sound. So that'll be a review for students who were in my class last semester. All right, but let's just go over a couple slides here. So oscillations and waves is the material for this week. I'll say a couple words about simple harmonic motion, sort of the canonical way of doing oscillations, and waves in one dimension. When I'm in presentation mode, I don't see what the chat is. So I just saw something happen or heard something say something. What was it? Oh, somebody lost connection. All right, hopefully you're back. Okay, so if you type something,
there's a question.
Say it again.
We can read it out loud if there's a question.
Hey, Kelly, can I deputize you?
Sure.
Could you read the comment out loud since people are shy? But
where they're relevant? Sure.
Yeah, if they show up, could you just read it out loud? That way I don't have to leave presentation mode. Thank you.
Absolutely.
Okay, so we'll go back to here. All right. So I'll say something about simple harmonic motion, which is the standard canonical way of describing oscillations. And then I'll say something about waves. Just a brief discussion of this. Okay, oscillations. So how do oscillations happen? Well, you've got something which is in an equilibrium position, and you push it, and it comes back. And then it kind of overshoots, and then it comes back again, and that's what an oscillation is in general. And it happens with everything. It can happen with my little lamp. I don't know if you can see my lamp now, but I can tap on it, and you can see that it oscillates back and forth for just a moment. So the simplest kind of oscillation arises when the force that brings the object back to where it was is a linear restoring force like this. And this is Hooke's law, which you'll remember from last semester. So this is the standard way that it is written. Force is a function of x is minus kx. But that formulation of it specifically refers to a coordinate system like this. Okay, so for simple harmonic motion, the sort of canonical way of imagining it is you've got a block of mass m sitting on a frictionless surface connected to a spring, and the spring is connected to a wall somewhere. And then there's some equilibrium position. So when the block is in the equilibrium position, the spring is neither stretched nor compressed. And then you've got this coordinate system, x. And in one direction is the positive direction. Here to the right is the positive direction. And in terms of this coordinate system, this expression of Hooke's law makes sense. So in particular, if x is 0, then the block is located here in the middle, not where it's shown at the moment, but here, and there's no force. So that makes sense. If it's in the equilibrium position, it's just going to sit there. If I move it to the right, as it's shown here, then x, its position coordinate, is a positive number, and I plug in a positive number here, and this minus sign indicates that the force points in the negative direction, which is to the left, which means that the force tends to bring the object back to where it started. And similarly, if I move the object to a position over here on the left side of 0, since I said that to the right is positive, that coordinate would be negative. If I plug that into this formula, I have a negative negative, which means a positive. So the force points in the positive direction, and that would tend to bring the thing back to the origin. Okay, so that's Hooke's law, and it says that the force is proportional to the stretch, the position of it away from the equilibrium position, and K is a spring constant. It's a number that tells you the stiffness of the spring. Right? The bigger the K is, the stiffer the spring is. Okay, so if you have that set up, here's this video, which all right, so I'm going to do this. Go and share. Where is it? Share the screen. I'm thinking out loud. Here it is. Okay, hopefully you see this little YouTube video now.
Yes.
Everybody see it? Very good. I like this video because it gives you a visual, something to have in mind visually as to what simple harmonic motion is. So the yellow cube is the block, is the mass. You see the spring there, and it just swings back and forth. In red is the restoring force. That's the force that the spring exerts on the block. You see how it switches back and forth. You see the other forces. There's the weight, force of gravity on the block, and there's also the normal force from the surface on the block that's upwards. That's the upward arrow. The little dots that are sort of migrating up to the top of the screen are just sort of indications of where it was at any given time. So there's a black dot wherever the block is, and then it moves up so you can see sort of a history of where it was. And you see that it swings back and forth.
Dr. Barreto,
yes.
Elastic energy, is that the spring potential energy? Is that what
Yeah, I'm about to talk about that thing on the right. So on the right is a depiction of what the energy is, and I happened to stop it at just the right moment so that the block here is all the way to the right as far as it'll ever go. So it has stopped at this moment. Actually, it hasn't even moved yet now that I see it. I went to the beginning of the video. So it's all the way to the right. The spring is stretched to the right as far as it will go, and all of the energy is in the spring. And so that's why this is green. It says elastic energy in green. So all of this energy here is green. And now, when it's let go, you'll see what happens as it moves. So there it goes. See how it switches between kinetic energy in red and elastic energy in green? So I'm going to stop it about there. Okay, so I tried to get it right in the middle, and I wasn't able to do it. This is a little bit past the equilibrium to the right. Most of it, as you see, is kinetic energy, so it's moving pretty quickly. The spring is only a little bit stretched, so there's only a little bit of elastic energy, a little green at the top of that column there. And then if I let it go again and go to the other side there, okay, so now the spring is almost maximally compressed, not quite because there's a little bit of kinetic energy still. It's still moving to the left. But most of the energy has gone into the spring because it's compressed there. Julia, did that answer your question? I think that was Julia, right?
Yes, you did. Thank you.
Okay. All right, so this is what you should sort of have in mind when you think about simple harmonic motion, this sort of standard thing. Okay, go back to the PowerPoint now. Juggle everything around. Okay, so PowerPoint should be back, right?
Yes, it is.
Okay, thank you. All right, let's go over a little bit of terminology. Let me get some water. My voice is a little heavy today. Some terminology. Okay, so here's a little picture of that block and spring system, and I have a couple snapshots of it. Here it is at the equilibrium all the way to the right, back at the equilibrium all the way to the left, back at equilibrium. So in this case, time is going downwards. And I've shown one cycle. A cycle is just one trip back and forth from wherever you might pick to whenever it gets back there. Whenever it gets back there and goes in the same direction, I should say. Okay, so you could graph the position as a function of time down here. You see I have x position plotted vertically and time plotted horizontally. And one cycle looks like this. So here I started at x equals 0, and it went to the right, positive x, then back to 0, went over here to negative x, and then back to 0. So that's what's shown here. This cycle, that's one cycle. And then, of course, it just repeats. Here's another cycle later in time. There's another cycle later in time. Okay, so so there's a graph of the thing in time. And if you've got simple harmonic motion, by the way, this plot of position versus time will be a sinusoidal thing. It'd be like a sine or a cosine or one shifted in time, one way or the other. Another word defined as amplitude. Amplitude is the largest displacement measured from the equilibrium position. So on the picture up here, the amplitude is there. The distance from the equilibrium position to the maximal distance away from it. Here is the positive A direction, here's the negative A direction, but A itself is a positive number, telling you what the amplitude is. And on the graph down here, A is this tick over here, that distance. And if I put another dotted line at negative A, then you can see that's the maximal displacement in the negative direction. So these red arrows are indicating the amplitude, these little green things. Right, so simple idea. Since amplitude is a distance, it's measured in meters. Period is the amount of time it takes to do one complete cycle. And universally, it is depicted with a capital T. So the time on this graph of position versus time is the amount of time between, say a peak and the next peak. Since this horizontal direction is time, that's the amount of time. But it could be between here and here, for example, and here, because it just repeats, right? From wherever you are at one point to when you return to it going in the same direction. And I said going in the same direction because notice that at this position, you get back to it here, but you're going in the other direction. So then you come back and there you are again. So that's one period. Period is time, so it's measured in seconds. And then frequency is the number of cycles that happen per unit of time. So in the amount of time from here, the origin to the end of this little time arrow here, we've got 1, 2.5 cycles. So frequency is 2.5 cycles per that amount of time. And here's a different oscillator with a different spring, a stiffer spring actually. And you see that in the same amount of time, this other oscillator has got 1, 2, 3, 4, 5, 6, and like 3/4 of a cycle. So that has a higher frequency. More things happen per unit time. It oscillates faster. Frequency is just the inverse of the period. And so it's measured in inverse seconds. And one inverse second is called a hertz. Mr. Hertz will make an appearance later in the semester for a very important contribution to the physics. And then one interesting result is this, that you can express the period of a simple harmonic oscillator in terms of, if you're thinking about it in terms of a mass on the end of a spring, in terms of the mass itself and the spring constant. So 2 pi square root of m over k. So I won't derive that now. I'm sure you'll do that in the rest of the class. But this is a useful thing to have in mind. And in particular, it's interesting because the period does not depend on the amplitude. The amplitude, A, is not in this formula. What that means is that, say, if I look at this oscillator here, and I pull it over to that position and let it go, and then it just oscillates back and forth with that amount of amplitude, I could measure what the period is, and I could see that it's so many seconds, whatever. Then I could stop it and grab it, and instead of bringing it to here, I could bring it out to twice as far and let it go from there. And then it'll oscillate back and forth with twice as much amplitude as before. But what this is saying is that the period would be the same. The period does not depend on that amplitude. And that's kind of interesting when you think about it. Some people might have guessed that it would depend on the amplitude, but because we're talking about simple harmonic motion in particular, that the restoring force is linearly dependent on the displacement, the period does not depend on the amplitude, and that's why simple harmonic motion is a good timekeeper. When you have the pendulum in the grandfather clock, you don't have to worry about how far you pull it to the side. It's going to keep pretty good time. And you'll remember that that depends on it being a small angle. Okay, so I want to move on. Wow, time is going quickly. All right, wave motion. So I'm going to go on now to wave motion. Here is a string, and it's pulled taut, and you can do this wave pulse. Like you can take the end of the string, and you can just sort of give a flick, and then you get this little bump, and the little bump moves. It's a wave pulse. And that's the kind of phenomenon that underlies the idea of wave. You could do it repeatedly, and here's the top view of a string that's on a table. You see the little table legs. And the guy's moving his hand back and forth, and you see a bunch of wave pulses that are moving to the right. They haven't gotten to this part of the string yet, you see. So wave travels along its medium. In this case, the medium is the string or the rope. And notice that you've got this shape that's moving to the right, but what the string is doing is it's just moving up and down. Like this little, let's go to this little chunk of string here. See how it's sort of chopped up into little bits? Look at that one right at the top. That little one at the top is not moving right or left. It's just moving up or down. The ones here have not yet moved up and down yet. When the wave gets to it, they're just going to go up and down and up and down. So as a result, there's a difference between the velocity of the rope particle, which for this one at this moment is up. It's moving upwards. It's going to get to the top when this one part of the wave gets to it and then start coming back down. That velocity or that speed is different from the velocity of the wave itself. The wave itself is this shape moving to the right. So those two speeds are not the same. Have that in mind. The important property of the waves is that they transmit energy and information. So if somebody is holding the other end of the string and they're blind and they can't hear anything, when this wave gets to it, they'll receive a signal and they'll know that somebody sent a wave. So they send information. And they could put a little tiny mass on the end of it, and it would jiggle back and forth, and they could receive that energy and maybe do something with it. So waves transmit energy and information, but notice that they don't transmit rope. In this particular case, none of the rope is actually moving to the right, as the wave does, because the rope, all it does is move up and down. So they don't transmit the medium, but they do transmit energy and information. Okay, so here's a drawing of wave motion. And it kind of looks like the drawing I had before, but it's different because now the x-axis is space, it's distance. So you can imagine that this is the shape of the rope at any given time. And so there's more terminology then. So over here, the rope has not yet moved at all. The little chunks of rope haven't gone anywhere. Here, this chunk of rope has moved to the top. Here, this one went up and came back down. At this particular moment, it's back where it started, etc. So continuous waves start with vibrations. That's vibrations of the chunks of the rope. If the vibration is specifically simple harmonic motion that we described earlier, then the shape of this wave in space will be sinusoidal. It could be described by a sine function, perhaps shifting left or right. And then there are these terms. So amplitude is the same as before. This little chunk of mass of the rope does simple harmonic motion back and forth with amplitude A, depicted like that. Wavelength is a new one now, because the wavelength is the distance between this chunk of rope and that chunk of rope, such that these two chunks of rope do the same thing simultaneously. Right? As the wave goes by, this chunk of rope moves up and down, so does this one, and they're synchronized. The distance between those is the wavelength. The oscillation itself has the same frequency and period as before, but the wave itself has a wave velocity, as I talked about before, that's different from the motion of the actual particles up and down. That whole shape moves to the side, like this. It's this sort of very lo-fi animation. There's the rope, and you can pay attention to that little bit here. It's not doing anything, but then the shape goes by, goes up, down, up, down, up, down, and then now it's not doing anything. And that's what a wave is. Notice that in the amount of time it takes for a wavelength to pass, like this shape is going to go by, and at some point this peak is going to be here, and then at a certain amount of time later this peak is going to be there. And during that time, this little chunk of rope started out up high and then went down and came back up, so it did one cycle. Right? What that means is that the wave travels one wavelength during one period of the oscillation. Have the next slide. The wave travels one wavelength in time equal to t, the period of the oscillation. So we could write down this equation here. The speed of the wave is the wavelength divided by the period. But since 1 over the period is the frequency, you can also write it this way. The speed of the wave is wavelength times the frequency. This is very important, and it applies to all waves. Speed of a wave in terms of wavelength and period frequency is this. This will come in later in the semester when we talk about the speed of light. We'll have the speed of light on the left, the wavelength of the light, and the frequency of the light. You'll be using this formula a fair amount. And then finally, I have a little slide on speed of waves in chords or on strings in particular. So if you're talking about waves on a string that's stretched, you can relate the speed of the wave to physical characteristics of the actual string. In particular, the tension force under which the string is stretched. And mu here is the linear mass density, so the total mass of the string divided by its length. How many kilograms per unit length of the string it is. So you see that if you pull the string more taut, this force gets larger and the speed of waves on it increases. But if you use a heavier string, a thicker string on the guitar, then this mu is larger, and since it's in the denominator, the speed of those waves would be less. And if you're so inclined, you can check that the units of this thing is actually correct. So newtons for the force and kilograms per meter for the mass density. Manipulate that and you'll find that it's meters per second after you take that square root. Okay, that's it for my little PowerPoint. Any questions at this point? Still out there?
Yep, still here.
Okay, I don't hear any questions. All right. I'm going to now leave
We've
PowerPoint.
so far.
Come back to here. There's a chat. Okay, great. 31 of you are still here, so thank you. Great. Okay, so what I would like to do now is give you a couple of. I will post this. Yeah, I'll post it in the Blackboard that we have here. I'm going to give you a couple problems to do. They're very easy. I think you'll find them very easy. Now, what's the best way to do this? That's what I'm. Do you guys want to break into groups? I've never done that on this. Let me do that so that I take a moment to figure this out and see if it's worth doing later. So forgive me, I'm just going to randomly break you into groups. I'm going to make 9 groups. There'll be 3 groups of 4 and 6 groups of 3. And you'll just be in there for a moment or two while I give you some problems to work on. Yes, we'll come back. And if there's time, then we'll go over them. Otherwise, I'll just post a solution. Let's see how this works. All right, so you should all be in. Can anybody hear me? I'm in the main room. You probably cannot see me. All right, so now let's share the files. Okay. Problems.